Hey, what's going on? This is Jun-chan. We're back on stream with more Comonadic Explorations. Let's just jump straight into it. So let's see. Let's do a little bit of our housekeeping. Last time I was complaining about not having switched to Chrome for performance reasons. I mean, and also not being able to do my use the extensions, which maybe I don't even have, or I don't have it here, the copy paste extension. Hey Hoss, thanks a lot for the follow, really appreciate it. Yeah. So yeah, I did this this browser change, so I haven't transformed or brought my tabs from my hundreds of tabs from Firefox, but that's fine. So what are we doing? We last time we were playing inside this lvs.pers file. So let's go check it out. And that is this one, yes. And yeah, we imported the LVS monad from the Essence of Data Flow Programming, sorry, LVS Comonad from the Essence of Data Flow Programming paper. And we were trying to see whether actually this Comonad had the same extend as the one that Kenneth Forner uses in his Comonad sheet. Oh yeah, I'm not logged in, so let me log in off screen just so that I can actually have the usual dark theme. And the second factor. Okay. So what do I have on line 65? Ah, yeah. I have this instance for tape. And basically, tape is very similar to LVS, right? Because tape is two streams with a focus A in the middle. LVS is an LV, which is a list, and an A in the middle together with a stream. So it's almost the same, but it uses a list on the left because the idea is that it's not really in practice useful to go towards infinity back in time. However, it is useful to point to something that will maybe come like a way long time, in a way long time. That's how I interpret it anyway. And so right, so the instance of Comonad for tape is one thing, and the other is for nested. So let me pick up right there. So yeah, one thing is that actually the Comonad instance for tape is fairly standard, but maybe we'll want to unfold it a bit just to see whether we get anything similar to that. And then here we are going to also maybe want to clarify it. So although this looks a lot like what iterate is like, I think prev dump, it's duplicate, yeah, it's yeah, duplicate of previous and duplicate of next. And you know what? This makes me think of the trick to make, indeed to make, what was it? To make tape traversable. And I think that was on Stack Overflow. what did it use? I mean Haskell, right? And streams. And yeah, that doesn't seem to work. Also, let's change to English. Okay, I think I had this in one of our previous logs. Where was this? Okay, is this one? Yes, I believe it might be. This post, yes, productive, and I think it's in part 2 that the instance is shown, and that's this one, and it's to make traversable on a tape, and U is that tape, with a left stream, a focus, and a right stream, to make that productive by making it ZP. I wonder whether iterate actually serves the same purpose here. Move left, move right. Maybe the fact that these are functions will actually work. Oh, I don't know. Right. We're not talking about the traversable instance here. We're talking only about duplicate. So maybe it was distributive here. But yeah, what we know is that Kenneth didn't end up using traversable exactly because there was a conceptual question around whether infinite containers could be traversable. And Ed seems to think that yes, as long as they're productive, which is kind of where this productive thing is about. And that's the Stack Overflow post, and that I think is where Ed discusses with Comonadic right here. We use infinite traversals all the times. Yeah, so what does this mean for where we're at? Several things, but I don't know whether I want to explore any of those right now. Yeah, one thing is that if we want to make this work in PureScript, then we will need to actually include laziness explicitly. And I don't think there's a way around that that I can think of to make things productive. Yeah, I'm pretty sure like we need to do that. And what did we have? Yeah, we then explored how fix which was the whole point of Kenneth's talk, which was to make fix performant by doing memorization. And he came up with this particular duplicate instance for this nested data type, such that it would work well combined with a regular fixed point. And where it ties in back to my interests is that this feels like a fold in time, and or rather, well, Kenneth used his fixed point approach in a way that was able to both advance and sort of fold in time, as well as use this reference to cells in a way that would actually converge to a fixed point, and use sharing in order to be more efficient. So how does this apply to what we're trying to do? Going back up the stack here, is we're trying to see whether we can understand the comonadic aspect of folds, and use the tricks that Kenneth uses to make them fast in PureScript, which is a lot of complex stuff, but that's kind of where we are. And to get back to that, I need to do recursion schemes, and from Comonads, that's the one. Okay, so let's pick it up from this side, I think, and so that we write a little bit more code, because next time I think in order to get this to actually run on PureScript, it's going to be a little bit tricky. So because of laziness, and because, or mainly because of laziness, and because of how well, how general this approach really is in terms of trying to mix like multiple dimensions of that sheet, including dealing with one of these dimensions as being time. All of this is, and the fact that this is true of repeat here, and so it made me wonder whether evaluate was a catamorphism. So sorry about that. I think in order to get back to bridge that gap, it's going to be easier for me if I try to, if I have some running code that's compiling, and that I move my way towards that. And so let's see what are the things that we were trying to do here. We were trying to use this prod catamorphism. I think these are, these came from not from recursion schemes from Comonad. I think this came from the examples of Matryoshka, which is where the recursion schemes live in PureScript. Recursion schemes, Matryoshka. Examples. So those are what these are. But I think I was trying to see if I could look at prod, which is an algebra of listf int into int, and see whether I could do the same thing for lifted well, for an algebra in free that paired free and coempty. So, and I'm not sure about, I think I was trying to see whether there was a pairing there, but let's find PureScript Matryoshka first. There we go. And right, I think the inspiration came from the algebra type class, or not, maybe from maybe it's actually just from Matryoshka. No. Let's see. Recursive. Yes. So Matryoshka, instead of using that base functor as is used in the recursion scheme library in Haskell, instead of using base, it's using this recursion type class or recursive type class. And when doing something like a fold, it is using recursive in order to using the fact that T is recursive and that we have some well, in this case traversable F, but I think G kata M is a bit too powerful for us. This is what we want. We want to try with kata for now. And so kata of an algebra, I think so. It's actually hard to see. Yeah. Okay, let's reset. So kata of F being an algebra of F2A, we'll take a T, which is traversable, and I'll put an A. So that's kind of like fold map, isn't it? Let's pursuit and look at the type of fold map. Yeah, it takes an FA and it returns a B. Given, oh no, sorry. Yeah, it takes an FA and returns an M. That's a monoid. And of course here A doesn't need to be a monoid because we just need to have a way to build an algebra. And I'm sure there's a correspondence between that monoid type class and an algebra, but let's not think too much about it right now. So here, what I wanted to do with prod prime was to try and understand what this recursive co-free and recursive free instances for recursive were, because it felt a bit like they were related to pairings. But I don't know that for sure, and maybe I shouldn't go too much forward into this particular rabbit hole until I really need it. So let me comment that out and maybe make a note, trying to understand the recursive free instance. And I'm going to also make a note in prod prime up there. And I think this prime can be safely commented out as well. Although that's not an algebra, okay. Whatever that means. But what we were trying to do is use this instance. Not clear what we can do with this instance, but when I squint, it looks a lot like a pairing. Investigate later. I'm going to write this in the log so that it's at least somewhere. Matryoshka examples, and here a pairing. Okay. So that should allow us to go back to trying to follow the blog post, hopefully. So here, if we compare where we have kata is of type recursive TF algebra FA to T2A. So I think algebra here is base TA to A. So it's algebra, and let's also unpack the type of algebra. All right. And that's just this. An FA to an A. And with kata such that we have some way to recurse T over F, which makes me wonder whether this is a distributive thing again. So we have instances for T as mu F or nu F. And let me try and right, and then we define list as list over fixed point mu. And so now we have a recursive instance for that. Okay, let me say that again. Kata takes an algebra FA, which for us is going to be this prod, which is something that can transform an FA into an A. And in our case, it's going to, so by taking int as the carrier type, we can output an int, and the way we define this algebra is pointwise in the fixed point, such that we can say that multiplication by nil is 1. So that's the product. It's actually the product monoid, so there is definitely a relationship here. Because if we do the sum monoid, then we explain what 0 means and what adding means, and then we have a sum as well. So the fact that that fold map takes a monoid here means that this A to M can be expressed in terms of an algebra with the sum monoid and the product monoid on it. Okay. And so we have this algebra. And because we give it a T, because we give to kata a T that is a fixed point in mu, then we know how to recurse, and kata knows how to do his job of getting an A. Okay, so that's fine. And let's read a bit more. So the carrier type is a plain old A value. So let's ignore para and histo for now. Three value don't seem to share any essential similarities, so usual trick of trying to see that actually there's some kind of transformer here. And in this case, it's a transformer of base T and, well, either identity A, tuple, or cofree. Which represent a container or context that holds further A values, which fit this idea of maintaining state, which was sort of, popping back the stack once more, The idea is where we were trying to, instead of using store T. Oh yeah, for a second I thought that store T could be used as a comonad to pass to string state through, but that seemed to be very misguided. And so I decided, I think, to put that aside for now and try and see what is the more principal way to build stateful iteration with a comonad and the recursion scheme. And then hopefully I can find a pathway to reconnect with the whole Comonadic UI topic. Trying to break down the problem. Okay, so what's pretty unclear at this point is how we're going to get our type class recursive TA to be some kind of transformer. That's really going to not be easy at all. Interesting, but really tough. And actually, interestingly enough, though, here we do have some inklings of things being parameterized with a further yeah, with a further depends a bit on coenv. I need to look at coenv again. If this is using the normal notation of this being also a comonad if coenv t is a comonad stack transformer, then maybe we have something that's a bit transformery here that maybe we can use. But let's first look at this coenv t definition again, and that is in pattern. And coenv t em, and so E is either I think this name is really strange, and I think that it's not a transformer. I mean, maybe if we squint, it's a transformer, but I don't think it's a transformer in the way that we want. So it's going to be pretty tough to get a recursive T, basically. Yeah, I really have no idea on how that's going to work. But maybe we can see whether the recursive TF, maybe some of the more generalized catamorphism here, even maybe kata M. Like kata M has a monad M there and an algebra M. So that's a monad transformer actually, right? That allows to have, yeah, to return into MA. And here with the comonad W, that looks like maybe that's going to be what we're interested in here. Interestingly enough, actually, there's also something that returns in an MA. So let's first, I suppose, try and make things work in a GKata. And this relies on GAlgebra. So let's see what GAlgebra is. And GAlgebra in a comonad W is something that is in FA, but is able to unwrap the W, which means just that it's able to extract, right? So, and it needs a distributive law between F and W. So that sounds a lot like, I think, what happens then later here in having a distributive law. So I think this is GCata, and it's dependent on W. So let's try to just write pretty much the same as this, but for GCata with the GAlgebra. Okay, good. We don't have to do too many crazy things. So let's try and write prod prime, which will be a GAlgebra. It seems like maybe GAlgebra, and we are going to want it to be an identity if we for start. And f is going to be list f int, and it's going to go towards int as well. And then for it to be so, we need it to be f, a function of f from FWA, so from FWA. So, oh yeah, right. So it's going to be either nil or prod prime of, well, and then it's going to also equal 1. Or it's going to be cons of, and then which side would it be? That the W, is it going to be WH and WT? Or is it just WHT? I think it's probably WHT. In which case it's going to be extract WH times T. We can try that, and then we can pass GCata prod prime and some list. Just need to import GCata. So maybe it's actually like so. H multiplied by extract T. A non-value WT. Maybe, but GCata is going to give us back an A. Identity int, yes. So we're going to need to unwrap or run identity maybe. We do import, data.identity, and let's go to definition, and or maybe we just use the new type instance and run it. I think we might have to do that. Yeah. Or unwrap it, basically, right? Let's unwrap. Okay. Another what? Could not map. Oh, does it need to be a list identity of A? I don't think so. There must be something wrong here. Let's see. GAlgebra of a comonad. That I think is fine. We need a distributive law between F and W. So between list F and identity. Let's look at what distributive laws we have accessible to us. And this is a type class. Oh, it's not a type class. Oh, no, it's not. Okay, okay. So in that case, indeed, we're going to have to pass it. And it's going to be... is that true, though? Yeah, no, it is true. We need to pass a distributive law. And I suppose we want to pass distributive law F identity. So dist kata, I think. And we can't show... Oh, I see. I think we're going to need to actually... well, do we actually need to unwrap? Maybe we don't really need to unwrap. Ah, there we go. Let's see whether we made that work, actually. Please keep pairing, Comonad playground, Spago run. And it should say 2424. It does. Okay. So here we're kind of in the recursion scheme from Comonads sort of already. But let's look at what this is equivalent to in the blog post. 0 for distributive laws. Dist kata, oh, there we go. G kata, dist kata is basically kata. And so the way in which we now are able, in theory, to use other comonads than identity is by continuing a bit down there. So W algebra is actually G algebra, I think. Oh, interesting, there's recursive here. So recursive is something that also exists here apart from base. I didn't realize it did, but okay. Glorious G kata, blah blah blah. G kata, dist kata. So kata equals G kata, dist kata. We have that, and then same for the other thing. And then he baked a application-specific, type-specific distributive law for his ledger data type. He defined up there, and yeah, defined a dist ledger in order to map around things. So that's in the case that we want to use a custom comonad, right? And so maybe we should play with exactly that that example. How about that? So let's go for it. Recursion schemes from comonads. Okay. So that we have, we do want a comonad instance. So we can write one, comonad ledger. Although I think we need extend, so we're going to need to do the trick I think I use for LVS, which is that, why did I end up hiding it. I think I might have ended up hiding it. That duplicate is fmap something. Is map f duplicate. No, that extend is map f duplicate, I think. Package Comonad duplicate. Right, duplicate is extend ID and extend is fmapf dot duplicate. So if we do extend of an f, it's equal to mapf duplicate where blah, and deriving doesn't work, but derive instance should work. Derive instance functor ledger. Yeah, except so if we get such env, such an x, then I suppose we just put ledger on in the front of it, and we're good. That, or maybe it's the other way around. It might be the other way around. Yeah, I think here we're just saying if you have a ledger x, then just return x. Okay, functor ledger, or maybe functor ledger tf. Let's go back to this. Yeah, I think so, right? But we need env. That's from the env comonad, okay. So hopefully we have it. Yes, we do. And functor actually seems to just work, maybe. And right, and then it's instance extend ledger, extend ledger tf. And we just need to is it not extend? Should be. Okay, just apparently we don't import Comonas. We just need to import class extend here. Not sure why it wasn't appearing. And set variable t for tfa. And this should be tf. Our ledge, well, maybe we'll have to write that one down ourselves. No type class instance was found. Oh, right. I think, yeah, that for given that f is a functor f, and maybe that's the other way around. Oh yeah, that's true here, and that's true here. Yeah. Oh, okay. Well, that all compiles, so that's nice. And then I think, yeah, we're going to need to do some Comonad stack transformer things. Let's see whether we need to do that, but we might need to do that for writing this ledger properly. I believe that's probably the case. And obviously, this is knowing that actually there is a more generic solution to inferring or automatically calculating this ledger, but I do want to see whether I can actually make this work properly before I try the more automated way. Okay, so here we'll want some for all TFA, and here we go. I think that's where we need a Comonad, but we and this is going to be map, and it's going to be map here as well. We're going to need co-free, and we need this histo, but I suppose we can import that. Yes. And well, apparently importing it didn't work. Oh no, it did. Okay. And co-free cannot be used in a pattern. Yeah, so that's a bit sad, but I suppose the way it works is that we do, we're here, we're ignoring the x, so so here we have w, and we say tell w, I think. ft, apparently ft, we can't pattern match properly with ft, so suppose we're going to have to go to the definition of ft. It's a tuple, okay. Yeah, no worries. So ft tuple blah blah, and we can remove that w and tell w here, and tell is from co-free, but that seems to work. Okay, and here same thing, we're going to need to tuple and then co-free, and here finally we want Comonad ask for ledger, so indeed we needed that thing, we needed these two instances here. That's Comonad env ledger, and that's Comonad co-free ledger. And we just need to import these guys. Okay, apparently not like so. Dot class, and I suppose class Comonad env, and Comonad co-free. Yeah, we should have that, right? Dot class and class Comonad co-free, and fmap is not a thing. And what do we have here? A local. So that's for Comonad env. Let's check out pursuit and see what Comonad env requires. Members is ask, and Comonad env has members It's actually members local. Ah, yeah, Comonadic ask is what we're defining here. Yes, I remember that things are just a little bit different as always in pure script. So we need Comonadic ask, and really here we're getting local. I mean, this is re-exported, so actually this is all from the same place. There's no such thing as this, but here we are really writing Comonadic ask, and I think we should be happy with that in order to be able to do ask, which is what we want. And indeed we are. And however, Comonadic co-free, what's going on? We need unwrap co-free, and so that's what it should be. Yes, I suppose unwrap is a different thing, and we need to import it from Comonadic co-free class as well. And still says it's unknown. Hasn't it been imported correctly? Probably not. Okay, because we have multiple co-frees here. So we are going to, well, yeah, that seems to be fine. And then we need unwrap. We need unwrap co-free, but we do have it. What's going on then? Oh, type variable A is undefined. Okay. Well, to be honest, we don't need that or that. And we compile. So that should mean that we're able to run the example with the disledger distribution law, meaning do Gketa disledger. Oh, apparently there's some issue with dealing with base functor. So we need another disledger to do something else in order to do our histopara thing. Right. So here, I mean, I've been a little bit dumbly following and copy pasting the code here, but now I'm starting to get a bit closer to what the meaning is. And here, basically, we don't have a fold at this point. I'm not sure how we would include a fold, but we have a we have something that does an isomorphism and something that does a paramorphism. I think a paramorphism is a map. You know what? I'm not even sure. Let's look at the so those are the folds. Let's look at the documentation here. It's going to be easier. Pursuit. And yeah, so transform refold might be those are the hilos. Fold we have kata and para. But para with tuple t. Okay, I need to maybe look at the recursion schemes library. Maybe it's explained. Yes, I bet it is kata, and that is for fold. Fold by far the most common recursion scheme. Working one layer at a time is the most common strategy for writing a recursive function. Those are rarer strategies. So fold is catamorphism. Give is base TA to A, argument special name, base T algebra. More generally, a function of the form fa2a is called an F-algebra. Names might be intimidating at first, but using standard nomenclature has benefits if you program with other shared vocabulary. Rest of this module lists a few of the other recursion schemes. Okay, so kata a with effectful, with an F, so some kind of transformer, para. Recursive positions also include the original subtree, in addition to the result of folding that subtree. So that won't work for time, of course, because it means that we need a finite container for this. Whereas possibly we can keep kata productive, maybe, if we can work that out. Maybe with laziness it will just work. And then histo variant of kata, which includes the result of all the descendants, not just the direct children. Like para, subtree is provided for each recursive position. Each node in that subtree is annotated with the result for that descendant. Let's recreate GitHub's directory compression algorithm. GitHub displays source data function, not src. GitHub does it because src only contains one entry data. So roll up 1 not foo, 2 not foo bar Excel. Not foo bar is just foo bar. So I think this applies when looking at, yeah, Cofree as a tree. I thought that this was if, I think Cofree of list is a roast tree, right? Here I have Cofree of tree F node. Tree F being defined earlier on in the examples. Some list F. Okay. Bin tree F is a thing. A tree F int. Each recursive position contains a string resulting from recursively folding the corresponding subtree. Yeah, I think tree F is lists, I think. And these are roast trees. And basically, I think histo tells us that we keep at any given level, we also have access to the whole subtree rather than have access to the whole tree. We have access to the subtree that we're focusing on. So that's a histomorphism. And then a zygomorphism is not defined. And Ana is the reverse of a kata, so it's unfold. And I'm not sure whether we want to build our Comonadic component from that, because we do have a Cofree in there, right? In our counter, I'm going to need to bring the the relevant types here. So W in our case is free counter interface. Well, here within a store T, but I think we'll probably have to change that. But that we end up having to build this co-free with the differ co-free, which I think is an anamorphism. But do we want to make that explicit or not? I mean, maybe because there's some anamorphism that cancel out with some catamorphisms. But then apo and future, I think, give access are the equivalent of, what was it? Para and histo. And so apo must provide the whole A structure at each, or the whole T structure at each step, and future must provide the sub tree as well, except here we're in free, not co-free, right? Histo is in co-free base T, yeah. So it's not really a tree, right? I think it is, but it's well, it depends really. Okay, I'll take a little break and I'll be right back. Okay, so let's zoom in on this idea of making of using these recursion schemes to thread state. So I suppose it really is the catamorphism, simple version of it, together with an algebra. And just using the identity functor is sufficient for that. So the identity comonad or identity functor. So if that's the case, then really we're not using a lot from comonads at all, using the identity comonad only. But maybe that's an essence of step-by-step folding, which works, I think, for, well, for time. But maybe having a paramorphism and a histomorphism could be useful for other dimensions. Like, is it the case that actually a paramorphism is what's needed if you need to access, like, have access to a whole spreadsheet? And does this make sense? Not so sure. At each recursion step, the ability to for your algebra, I suppose, to refer not just to the previous value, which is here, but to the any of the values in a row or in a column, therefore maybe in the whole spreadsheet. And then a histomorphism would make sense if we have also substructures that we want to focus on, maybe. So maybe doing more local calculations. Let's try with let's try the example. Let's see whether we can actually define a histopara. Let's go until the end of the example. Let's see whether that works or not. Let's see what type this would give us. A pretty intense type. So let's try W. Let's see. T342 is the W. So let's put the W here. Recursive FA, is it, or TF? Recursive TF. So that's T and T34. Oh. That's not what I was expecting. So that would be T, and that would be A, right? A, T. And then 343. 343 might be one of the, well, we need an F. And I think we're saying recursive TF and comonad W. Isn't that what we're trying to say here? It looks like apparently it's probably, oh, it's not recursive. I just haven't imported it. And again. Oh, right. GL, this is going to be a GAlgebra. FWA, or maybe FWA. Okay. And we are, yeah, that's going to only work for a ledger. So F is ledger. And so recursive T ledger. Does this make sense? Maybe it's TW here, actually. Possibly. Okay, I think I'm getting a little bit lost here. GAlgebra WFA. Okay, yes, indeed. WFA in that way. And recursive TF, I think. Recursive therefore T ledger. Maybe ledger T. How about ledger TW? GAlgebra T. Ledger T. W. I mean, that's possibly a type, but this is a type of what we want. Could this just be W? Okay, so you know what? Let's try the automatic derivation. How about that? So that's zero effort distributive loss, right? So I think we have disparity and things like that, right? In distributive laws. Yeah, we have disparity and desiguality and all these friends, and even this kata, and so we can combine the distributive laws, and so we can write a dis ledger by unwrapping ledger and rewrapping it and doing disparity and this histo. So maybe we do that. And does this mean that we then don't even have to write this ledger or these instances, or no? I think we probably need to have these instances, but so it might mean that some of these distribution laws depend on the Comonadic, or they depend on CoFree for sure here. and for G histo and para depend on ft, which is not exactly ask, but is kind of close to it. But maybe that's going to be a problem that it's not a type class here. Unless there's a no, there's no such things for type classes that I can see. So we need an actual concrete empty or an actual concrete co-free. So that's not exactly going to work for what we're doing, I don't think. Right, and then he does the unfolds. Okay, well, maybe we don't, let's say we don't care about ledger, and that we, however, want to build our custom folds, or yeah, custom folds. Then what would this look like? So the problem here was this won't work because Matryoshka, and I mean, let's compare with the Haskell. I suppose the shape of the distribution law in Haskell and the type classes thereof. Is that in base? No. Okay, so that's been foldable. Dist kata co-recursive comonad. This histo has cofree also not as a type class. And para has mt also not as a type class. So maybe I'm wrong, and I should try. And I should write this ledger like so. Map, and I think this. Then we can import this and import this histo, and then maybe just allow ourselves not to have a type here. Indeed. And then we'll want to run this. Is there any example of running that thing here? I don't think there is. So So we need to build a ledger. So what would it look like? Would be something like very close to this, except that we pass this ledger, and then we need to kind of like a run ledger, something here, and some ledger. It would probably be a ledger of ints, maybe. And run ledger need to be well, yeah, we need to be a ledger of something specific, and go. Capable of recording past computations, go free F, along with the environment provided to each computation. So let's say that in our environment we have a string, and that our F in cofree F, that's would be the past computations that we record. So I think if we make this a tuple, then we have a list, I think. But an infinite one, right? If we make this, maybe we have a natural. So it depends a bit what we mean by past computations here. Or what we want a base function to be. Free. For histo, the carrier type is co-free base TA, representative and adaptive shapeshifting cache structure around the original T, storing all previously computed A values. So para, I think, is env and is therefore for us it's string. And so that's one single env. But in this case, we imagine it's actually also the type of, it's also the final type. But I don't think that has to be the case. In general, I think we can have a different type. Some ledger. T. Free F and A. Yeah, I think all of these things can be different. So T, go free F, I think we need to do tuple int. That would be some kind of list event. And then int as the final type. And then we need to learn how to build an empty. really it's a tuple of E and a WA. Right, that's the W. Okay, so constructor and a tuple of a string and a WA, right? Yeah. So, and where our WA is of type co-free tuple int int. And we need to put this inside ledger. And this has type co-free tuple int int. And to build that, we just need, so that's the base Comonad. So we just need a one of our old unfold co-free or something like that, or differ co-free. It's not co-free T here, so we can we could actually tuple, right? Yes, I still don't have a good intuition for how to build something like that well, but I think be 0 and more, where more would be a type co-free. Well, maybe we don't even need to say what it is, but it would be n plus 1 and go n plus 1. An A and a tuple of co-free FA a tuple of int. Maybe we do need this. We do indeed. And then we're missing some show instance here. But before we do that, we need to have a run ledger. Which is going to be the algebra. And so run ledger is going to need to be for gkata something. going to need to be a GAlgebra WFA. So GAlgebra, and then W, I suppose, is ledger. Ledger TFA 2A. And WFA, yeah, right. So W, maybe WFA? No. Let's see. GAlgebra. Opacity distributive law, which is an obscure thing. Ledger TFA, I think, is the W. So say that's the W. The F is going to be list F. And maybe even list F event. Yeah, right now it's going to be algebra FA. Yeah, so it is going to be list F event actually. List F event and int to int, I think. But maybe ledger TF. Although we'll want the F to be list F, won't we? Maybe not. Let's see. Let's try with list F here. See if it type checks. No, that doesn't type check. List F event. Yeah, that does type check. Okay. And how does that work? Let's go back. Is there any of these things here? Means of distribution. This ledger. Some kind of GAlgebra. But we don't bother writing it here. Okay. So what would it look like? We'd get a ledger of empty, of tuple, of some env, and some cofree. And so we could do something like, since we know that the env is actually string, because that's the specific thing, we could do length of string, couldn't we? Isn't there length for string? Yes, there is. Length of env plus, and then we could get the head of cofree, which would be 0 or something. But then obviously this doesn't terminate, at least with tuple int. So we need to do tuple maybe int, and put and have hold on, that's right. Yeah, so then we need to case on head cofree, and then if it's nothing, then we would return 0 and be done. But if it's just X, then we need to make it X and also run ledger or something, right? We'll have tell. What do we do up there? We just extract. Because we know we have an identity in there. So maybe we get ledger. In the tail, yeah, in the tail, we will have a ledger. So we do run ledger, I think, but maybe of tail cough. And empty. And int versus maybe int, indeed. Maybe int. Just and go, right, yeah, no, go doesn't need to be, this needs to be a just, this also needs to be a just, and then maybe we say we put a guard if n inferior or equal to 5, and then otherwise nothing. Right. Yeah, otherwise, yeah, that maybe then. No? Maybe with tuple maybe int. Yeah, okay, fine. Tuple, nothing. And then we hope that this is lazy, basically. And maybe int with int. right. Yes. It's just in the tuple that there's the. That seems better. And then run ledger blah, and we want to return a plus if we could, but apparently this whole thing has type int. Yeah, we pattern match on the GeoGebra of such a thing, which is that's not the same as pattern matching on the ledger. The GeoGebra is a function. Hold on. Yeah, no, okay. I think I just have too many ints here. Still not. Oh, right. It's actually a just of now where we need to pattern match is on the list here. No. Hold on, maybe this whole listf thing is wrong here. No, I mean it's fine, but yeah, no, of course it needs to be tuple maybe int. I mean, I could try with listf int, but oh yeah, then it would be but then it would be co-free of listf int, and I'm not sure what that would be like. So I think what I'm doing here is basically fixing this, and then I think I also need to transform this in that case. That's a bit strange, all of this, I'm gonna say. GeoGebra would be an FWA to A. So an GeoGebra of a comonad that's the environment. I mean, I think in the end we're not a GeoGebra anymore, is the trick here. Gkata, taking the distributive law. The distributive law being FG, FGA to GFA. It's any F ledger blah. No, not any F. The F in the middle. Let's try and write it. Seems correct. So if that's the case, then GAlgebra should be GAlgebra of well, I suppose this would work too, or what? Yes. So we can say GAlgebra of GF, and maybe we do need an A. No, we don't need an A. Yeah, and that's the F, so that does sound actually credible here. And then when we match, oh, we have at the external we have a tuple in the GAlgebra of the WF. That's one of the tricks here. It's outside, the tuple's outside, so we're maybe not considering the tuple inside. Hello, Hyder. PureScript VS Code extension. Let's go take a look. It's the pretty standard one, I'm pretty sure. PureScript IDE, I believe, is the one. Yeah. Uses the PureScript language server in the back. And how have you been doing, by the way? So I think you're very welcome. So I think, in fact, here we are pattern matching on a tuple. And the tuple, yeah, the tuple is the tuple of the wrapping functor here. So we either have, either have tuple just X and this, or so let's try this, or tuple nothing and some continuation. Okay, we can't use that in the pattern matching. And that looks right. Defer. Yeah, of course, because we need parentheses also. Well, we need parentheses kind of on everything, unfortunately, when we pattern match in PureScript. Okay, and then that's an int. Yes. Okay, well, so in that case, I mean, to be honest, we could make this just a tiny bit easier on the eye by saying that this is a just here, and then casing on the just. In a fashion like this one, And I suppose we could also add the length of the environment here. And what would be the problem there? That run ledger, that conf will need to be a conf will need to be echo free, but you're saying it's not because it's a ledger string, and I think that's true. I think here we have another ledger inside, and so we need to do get ledger here, but maybe that's not gonna work really. Let's see, Hyder, what do you say? I think you will start learning PureScript. Excellent. The only way to really learn FP is by learning and using a pure FP1. I agree. You know, I've tried quite a bit with TypeScript, including using the FPTS library, which is an attempt of doing functional programming in TypeScript. So with a lot of the things that you find in Haskell and PureScript, but in the end, it's just too much complexity, and the easiest for me, at least, to learn is to indeed use PureScript or Haskell. But the fact that PureScript compiles to JS makes it really easy. And some people deliver a caveat for backend development with PureScript. They say, well, you need to be ready for using Node on the backend, and that's not necessarily the ideal choice if your backend has any expectations of having good performance, because in comparison, Haskell is really hyper optimized. But if you're learning, then 100%. And also, if your backend doesn't need to be very performant, then that's also a potential choice to run compiled PureScript on the backend. Okay, so what is the type of L is one question. That's really good to know. Can we deduce it? Here it's a ledger string, tuple maybe, blah. So we know, we know that's an int, actually. Isn't it? It's a co-free int, so maybe we just extract it as we did before. Use the co-free Comonad instance. Yeah, and then that's what I thought, that there would be some kerfuffle here, but we can just not have a type signature. Although it would be nice to know what the type signature of this is. So let's try and get this correct. And so it might be letter TF to F. Okay, and so it might be F to ledger TF. Still not. Or we need a functor instance for F. That sounds reasonable. And then we need co-recursive for T and F. I think that's also reasonable. Co-recursive for TF. And look at this, I think we compile. Oh, no type class instance. For recursive, yes. Yes, so that's tricky. That means that either I'll need a because in the previous algebra we were, in some sense, I guess, using liftf int as the t, so as the kind of traversable instance, as the thing we were folding against, and that had a mu in there. Whereas now we need to mu around some ledger, actually. So here, is there a recursive instance for ledger? Gkata. There is not. Just erase functor. We need a recursive instance for ledger string tuple maybe int and tuple maybe int. Projecting being the thing that gives us just one of the elements we need. So actually, I think indeed I need to write one, and I think I can. Recursive ledger. We can try and make it generic, and that would be recursive of ledger tfa and or tf and f, where project. So what is going to be project? It might just be, so extract gets the, maybe it's the co-free thing. Maybe it's just unwrap co-free. Recursive T and F. Hold on, let's look again at what was missing. We want this. Recursive of ledger blah. So for a T, which we don't really care about. So maybe it needs to be TFA and FA. That sounds strange. I think we don't need the carrier type. Yeah. F is a functor. But maybe in reality we need it specifically for this instance. That's also possible. Maybe we can't write it generically. Let's see whether that's doable. And then co-recursive string tuple maybe int. And so that must be because of the, that's a bit complicated. Is it because of the GAlgebra? Where is that? Oh, because of the dist ledger. Which I suppose is because of like the dist para or the dist histo. One of these two, yeah. Dist para needs the co-recursive instance. This histo doesn't, just a functor instance. Okay, well, I suppose we need it. Don't know how to write it yet, but we will try. So, instance co-recursive ledger co-recursive of string and tuple maybe int. that's going to be strange. And also I need to know what co-recursive needs. Embed. And the type of that is it takes an FT and it returns a T. So it means if we have a tuple or maybe in string, return a string. Okay. Tuple of something we ignore and an S, or return an S. Is that what you're saying? Or for an instance. Oh yeah. That's that's a problem. That's actually a pretty big problem. Because there's no reference to ledger here. Yeah. I don't think that defining it on ledger would even work. And here it's because we use disparity after having unmapped the get ledger. But hold on 1 second. I'll be right. Okay, so let's see if we can figure this out in a few minutes. I've already streamed a bit too long. Right, so we're trying to use disparity, and well, I suppose if we if we create a new type around tuple, maybe int, and call this our list CF or something, then say new type list CF equals tuple maybe int with a constructor. Then I think we can say that this is the CF. Maybe we want to make it an A here. That'd be nicer. Then it will look a little bit like like our previous algebra. And so then that should allow us, where we're going to need to rewrite some of that stuff as this cf int here maybe as well for the run ledger. That's going to be with one more parenthesis here, and this is going to be like so. And yeah, and then co-recursive would be on this CF, and then we can just pattern match here on list CF and the tuple, and that should make us fairly happy if we have the correct syntax here. And apparently we can't match a kind. Maybe, oh, right. Yeah, good point. So maybe int and a, is that? No, I think this is the functor. So hold on, when we do listf int in the G algebra here, or maybe that's not the right way to think of it. Maybe I should just call this, I mean, let's double check whether this works or not. So for you, it's still an orphan instance. So maybe string is the problem. So let's call it label, new type label equals string. Well, label string, and then let's make this label and give it a shot. Ledger label. That must be right. And then string, yes, we need to put a label around this. And right. Well, let's double check whether we actually need to have this. If whether it's both sides of the no, it's just only the first side. So maybe this is going to work. And let's see if there's still one hanging around. There is. And this should work, and this should work. And yeah, we need to say label here. And then unwrap this. Well, I suppose I can make a new type instance for that. Derive instance, new type label, new type label underscore. Is that the way? No, I think it is new type. I just need to import it correctly. Let's try that again. Here, it's a class. Hey. All right, so we compile. So that's good. Actually, we might even be able to run our ledger. So let's try it and see whether things crash. Yeah, we have a maximum stack size problem when we build, and that's not too bad actually, because that's about something we wanted to fix, which is fix the pure scripts or deal with laziness basically. Comonadic fold from different angles. So what did we do? We implemented the recursion schemes from Comonad ledger example, and then what we need to do is fix the ledger example to not stack overflow with probably laziness. So we'll do that next time. That should give us a good isolated way, or more isolated way, to make laziness work for specifically, I think here, Cofree, the building of Cofree. So maybe if it's just MK Cofree, that's the problem. Actually, maybe it's not that hard. Like, hold on 1 second. Let me try with defer Cofree here. And hey, Hyder, what do I think of Clojure? Yeah, I really like Clojure when I tried it. And Lisps are, for refactoring and moving things around, do have a lot of benefits. But that's, you know, as long as you don't have side effects. And so that's where things, that's where having types sort of start to matter. May have a chance to get a job where they use Clojure, but not sure, since although it's an FP language, what bothers me is that it's dynamically typed. Yeah, that's right. No pattern matching. Yeah, that's true. But Clojure is it in some place of the design spectrum where it's still quite interesting because of its what's called its ISO. What is it? ISO iconicity. Is that the right term? I forget if it's exactly this, but or maybe auto iconicity. It means that each Clojure expression can create new Clojure expressions. That means that you have a macro language. Basically, you can do template Haskell infinitely nested. You can do macro languages infinitely nested in Clojure, and that's just super easy to do. So doing meta programming in Clojure is really super easy. But yeah, the FP purists, the people who like PureScript or Haskell, like myself, will tend to say, yeah, but the problem is that as soon as you start having fairly complex programs, then being able to reason about types start to be really necessary, because otherwise you don't have a compiler that's guiding you to solve issues and so on. So, or to even have abstractions that are useful to build bigger programs out of smaller, more understandable blocks. So when I tried Clojure, I really liked it. I thought it was very natural to program in it. It's actually not as easy. I mean, it's easier than to program in PureScript and Haskell. But I think that the reason why PureScript and Haskell are a little bit more difficult using types and so on actually pays off, because types are really helping to think about your programs in a way that really helps. So so consider it. I imagine that if you already have a chance to get a job, then maybe you need to answer that question for yourself fast. If that's the case, then spend some time reading some Clojure code, maybe even try a bit writing a little bit of Clojure code. You'll find also a lot of if you search on Google, like people comparing Haskell and Clojure, for instance, you'll find a lot of different interesting opinions about what are the pros and cons. But in general, it is Clojure is really nice to program because as a Lisp it has this meta programming that makes it really easy. But when it gets too complex, and then you can't really reason about your code so much because you don't have types, and PureScript and Haskell have types, and that really makes a whole bunch of difference. Yeah, anyway, I think I'll leave it here right now. Thanks a lot for watching. Heider, it was good to see you again. Good luck on making that choice. And yeah, come back on the stream on Thursday evening, same time, and tell me what you decided, if you've got more opportunity to move forward with that. All right, take care, Heider. Bye-bye.